everyone. Thanks for joining us today. Today we have Vincent. He's a PhD student at Technical University of Darmstadt and at TFKI, the German Institute for Artificial Intelligence. He's currently working on off-policy reinforcement learning methods. He works under the supervision of Jan Peters. Before his PhD, Theo graduated from MBA at ENS Paris Saclay. He also worked on computer vision problems in Parisian Lab and Saint Finant Lab. Also, he was a part of a Swedish startup, Signality. Theo did an internship in biostatistics at Harvard Medical School. Now I'm going to pass on to Theo. You can get started.
Hi, everyone. Thanks for the invitation, Rahul. I'm very excited for this talk. So in this talk, I would like to speak about how to optimize the learning trajectory of reinforcement learning agents. This title might not be so clear for you, and I will try to make it understandable. But most importantly, in this talk, I would like to argue that we can really go beyond the classical algorithms that we have in RL, such that we can optimize their learning trajectory. I know those things, those concepts might not be familiar to you, and I will take the time to explain them. So the first objective of this talk is to explain and to introduce the concept of a controlled algorithm. And then I will present some working example of what I define as a controlled algorithm. Just to make it clear, it's a concept that is new and that I'm introducing in this talk. It's not something that is has already been published in the literature and so on. So for that, I would like to walk you through the story of a reinforcement learning researcher. Feel free to interrupt me at any time. I'd be happy to exchange on some ideas and to answer some questions. When you think about it, the story of a reinforcement learning researcher starts with the classical reinforcement learning pipeline, where you have an agent and an environment. The agent is interacting with the environment with an action and is parameterized by a policy that has some parameters, theta t. And the agent gives as return the reward in the environment for the next step and the next state. Of course, this alone does not really work well because this is basically policy evaluation. So you usually have an algorithm that I call here phi that acts on the agent to actually change its parameters. And for that, it takes the reward that is given from the agent. This on its own constitutes the training process. And most reinforcement learning researchers, what they do is they try to come up with an algorithm by thinking like mathematically how it would make sense to design one and take the return out of it, out of the training process. Depending on the use case, the return can depend. It's not necessarily the return of the agent in the environment. It can also be the time that it took to reach a certain performance or the amount of samples required to reach this performance. It really depends on the use case. And of course, the main goal of any reinforcement learning researcher is to find this holy algorithm that is better than any other algorithm. In most cases, it's very hard, and it's not usually happening that you find an algorithm that beats every other algorithm on any benchmark. When you think about it, the thing that I'm speaking about now can be really synthesized in just another loop, basically, where you have a human giving an algorithm and taking back a meta reward. An idea one can have is to replace this human with a computer, and then you have a computer proposing algorithms that are evaluated in the training process. And then the computer observes this meta return and sees what happens. But unfortunately, this idea might take you a lot of time, even if you might actually end up having the best algorithm that no one has discovered so far. As I said, yeah, it takes time. So maybe no one wants to do this approach. But most importantly, if you look at the people that are employing you, they will see the cost that it needs to reach this algorithm and the energy consumption that it requires. So the question that I would like to tackle in this talk is, how can you find a good policy after only one training? This would be already amazing, you know, because you don't need to maybe find the best algorithm. You just want a good policy at the end. So why not just aiming at this goal instead of aiming at a good algorithm? And for that, for me, what we should really look at is the training process. So I'm gonna dive into the training process to really look at how it looks like. The training usually starts with a set of objects that you have in your computer. Let's say the initial policy, the data set, maybe it's offline, so you have a data set, the Q function that is initialized, and the state in the agent's MDP. Afterwards, you apply the algorithm that you chose, the one that you think could actually be very good. And afterwards, you look at the set of objects you have stored in your computer, so the policy, the data set, and so on. One thing that is very interesting is that you keep actually applying this algorithm to this set of objects. So actually, this set of objects could be considered as a state. It's basically the ensemble of objects you have in your computer. And this algorithm that you crafted is defining a transition kernel between one state and another one. So when I'm using the word transition training process, it's really not out of random. It's actually really an algorithm, a mathematical definition of the process, where you have a state space defined with some states. In this case, is the set of objects you have in your computer. And you have the transition probabilities that are defined by your algorithm. And you have a return that you can define. So it's the meta return. So it's a function of the return, the time, and the samples, basically. And this constitutes a simple process in the mathematical sense, where you have states, transition kernels, and reward. And now you can think about it and look at the fact that if you define the state space in a correct way, actually this training process is a training Markov process. And one thing that I found quite disturbing that everyone uses is the fact that training an agent, it's actually equal to evaluating an algorithm in this Markov process. So training a DQN, a PPO agent is actually evaluating DQN and PPO in this training Markov process. And this got me thinking, do we really want to do that? As I said, I just want a good policy. I don't really care about which algorithm I'm using. So if you represent the return or the meta return as a function of time, so here you have the time steps of your algorithm, and here you have your return. You came up with an algorithm that is very promising, that I represent here in orange. So you evaluate it. It goes very high at the beginning, so you are very happy. And for some reasons, at one point, it goes down. But maybe you would have wished to act in this training Markov process in a way that you would have changed the algorithm in the middle of the training to go for an algorithm that is actually better at that stage, yielding a good policy in a single training session, which means that in a single training trajectory or a single training, you get a good policy. This means that I'm calling for training Markov decision process, where each time in the training, you have your state, your meta state, ST, which is the set of objects you have on your computer. And instead of applying just one algorithm, you have the choice between applying several algorithms leading to several future states. And maybe with that, you have a chance to reach a good policy at the end of only one training process. Also, one note that I want to make here is the training, the controlling frequency of your training MDP does not need to be the same as the controlling frequency of the agent in the agent MDP. The training MDP can be controlled in a much lower frequency because things are happening less fast than in the agent MDP. So we were back in a problem where we had a lot of energy to spend and a lot of money to pay to something that maybe is a bit more hopeful, which I call a training MDP. Let me just explain carefully how this pipeline looks like. As I said before, we start with the RL pipeline. You have an agent parameterized with parameters theta t that are defining a policy pi theta t. Given a state, it outputs an action AT. And the environment outputs the next reward and next state, given the transition probabilities that are defining this environment. You have an algorithm that sets the new parameters of the agent, and the agent transfers the reward given by the environment. This algorithm is parameterized with an algorithm phi t, and this is seen as an action for a larger MDP, which is the training MDP, given a state and an algorithm or an action, if you want, you have the next state. Of course, as I said, those actions or those algorithms can change during the training process. So this means that you need to have a supervisor that is parameterized with some parameters phi. We're given the policy of the supervisor outputs the next action or the next algorithm to apply to your training process. And the supervisor can take the reward, but this time it's the meta reward that is defined according to your needs. So now the question that you might ask is, okay, cool, I see where you are going, but how to learn this supervisor, this pi of phi? Well, before trying to see how to learn it, I propose to see what kind of different settings we could consider. Either we can speak about the training MDP in the sense where you would like to learn a supervisor, phi, here, on some agent MDPs, so you would change different environments here, and you would hope that this supervisor that you learned generalizes to other MDPs. This is basically an idea that is very interesting, but it would require many training trajectories. So to train many times different agent MDPs to have a proper phi. So I propose to leave that away because the focus today is about how to learn a good policy in one training trajectory or one training session. So for that, I propose to consider another setting in which you control on the go without learning the supervisor, which means that you just see a stream of reward and you just control, so you take the next actions without actually learning a proper supervisor. Because once again, you are only interested in having a good policy after a single training trajectory. And this, as I said, requires only one training trajectory. This is what I would call a controlled algorithm, because during a training, you control your algorithm to actually make some modification to itself to yield a better reward, or basically to yield a better sum of meta reward at the end of your training. I hope now you understand a bit more the title which claims that we can optimize the learning trajectory of reinforcement learning agents. This means that I have already introduced the concept of a controlled algorithm, and I will go now for the presentation of working examples of controlled algorithms. If there's any questions, I think it's a good moment to clarify things, because now I'm going to go for the explanations of the examples. I'll try to see if there's any questions in the chat. I guess everything is clear, or at least there's no question. Okay, so I will continue. Yeah.
How is this different from meta-reinforcement learning?
Hey, that's a good question. I'm coming to that in, I think, 4 slides. But thanks for the question.
All right.
Cool. So I'll continue. Once again, feel free to interrupt me each time there's something unclear. Okay, so what about the working examples? I just want to make sure we are on the same page here. So I'm going to present examples that are trying to control a training MDP, where so a training MDP is not really looking different than a normal MDP. It's just that where the states are the set of objects you have in your computer. And the actions are basically the algorithms that you choose to modify the sets of objects you have on your computer. And the reward is simply the reward that you define yourself, which is, it can be the reward in the training MDP, the agent MDP, but it can be anything else. Cool. So the real objective that you are trying to maximize now is you are trying to find the sequence of actions or the sequence of algorithms that would yield a high sum of reward, given that you have a transition kernel that is determined by the state, the action, which is the algorithm, giving the next state. Cool. So in the following, I will present 4 working examples that actually showed that you can improve the classical RL algorithms to yield a good policy in a single training run. Okay, first, I will speak about differentiable dynamics, because I think it's quite natural, and indeed, we already had a question about it. So what you could think about when you want to solve this problem is to consider differentiable dynamics, which means that you can take the gradient with respect to the transition probability of your transition kernel, where here it's the algorithm, here it's the state, and here's the next state. And this is meta-RL, as you asked. It's actually a field that has been quite successful. And here you have actually the meta gradient. To give a clear example, you can think about it when you are not really choosing between different algorithms, but between different learning rates. What you can do to try to find the optimal learning rate at each time step is to compute the gradient with respect to the transition dynamics. So here you have, for example, the next policy, here you have the current policy, and you try to see how the next policy is influenced by the learning rate. This is meta gradient or meta reinforcement learning. And with that, you can optimize actually for the entire trajectory. So it's actually quite appealing. One big drawback with meta-RL is that you need differentiable dynamics, which means that you cannot cope with discrete action spaces or discrete algorithm spaces in this case. For example, if you want to do neural architecture search, so again, not choosing between different architectures, but between different algorithms, but between different architectures, then it's very hard because it's not differentiable. Cool. I just wanted to make a point here because I was really sure that this question was happening. In the following 3 working examples, I will present works that I have been working on during my PhD. Again, feel free to interrupt each time there's a question. Cool. Then I will go forward and I will speak about methods that are trying to maximize the immediate reward. What I mean by that is that there have been some methods already that decided to reduce a bit the horizon because they know that it's very hard to optimize for the following horizons, especially if you are not allowed to do more than one trajectory. So a very naive and maybe first step would be to maximize the immediate reward. We already know in RL that it's not a good idea because this can lead to very suboptimal behaviors. I just want to recall here that most of the algorithms, if not all of the algorithms developed so far in the RL community, are simply evaluating the algorithms. They are not controlling them. So what I thought about when I was doing my PhD is that already doing immediate reward can actually lead, in some cases, to better results. This is generally called population-based training, and I will try to explain why. So if you're not familiar with population-based training, I'm going to explain it now. Let's think again about what happens when you are in a state T. Again, a state is actually the set of objects in your computer, and you have the choice between two algorithms, phi and phi prime. What you really want to know in this case is to know which algorithm or which action is the best. Here, we're going to optimize the immediate reward, so we can even speak about a multi-arm bandit setting where you choose between different arms. So here, the question is which algorithm will actually lead to the best meta reward. And if you know the answer, you can just choose it and then go forward. So population-based training took a simple approach. You evaluate both arms, and then you select the one that you prefer. So for example, to really give a concrete example, you would actually select both algorithms, and then you select the reward as the performance of the agent in the agent MDP, and then you say, okay, this algorithm leads to the highest performance, let's take it. A field where population-based training is heavily used is actually when phi is not an algorithm, but a hyperparameter. This is a nice way to actually tune the hyperparameters of your algorithm. You select two different hyperparameters, you employ the same algorithm, but with different hyperparameters, and then you simply select the hyperparameter that performed the best. Okay, I hope you had a good overview of population-based training. This is basically nice because it allows you to work well with discrete action spaces or discrete algorithm spaces. The thing that is really problematic is that it's costly because it uses a lot of samples, basically. And for that, I really thought that we could do something better. So one of the contributions I did during my PhD is to try to remove this downside. Let me explain. Here, the problem is that you are really trying to evaluate each action, which costs a lot because you are relying on the performance of each algorithm in the agent MDP. But what if you would change this thing, so this definition of the meta reward, for using the training loss instead? In that case, you don't need to evaluate each action. You can just use, for example, if you speak about hyperparameters, you can train different hyperparameters, but only look at the training loss as a reward. So you don't need to evaluate each agent having different hyperparameters in the agent MDP. I will give you a concrete example on DQN. So let's speak about DQN. So this is the first time I'm really giving a concrete example where I'm going to explain the training process that a DQN agent is undergoing. So here you have, usually when you tune hyperparameters, you do a grid search. So you do multiple training processes. You start with a target network, so Q bar, and you apply the Bellman operator, R plus gamma max of Q. This is constituting your first meta state. And then what you do is you choose a hyperparameter. So this is actually our action space. Remember, here I'm just speaking about the baseline. So DQN is simply evaluating this hyperparameter. Let's say to make it concrete that we use Adam. So we actually reach another metastate, S1, by learning an online network, Q1. We do a target update, so we update it to be the target network, and we continue applying the same hyperparameter, let's say Adam. This means that actually this constitutes the training process, and at the end, you get a performance, the same as I was explaining before, with your algorithm, in which case it's DQN, but with Adam. And if you want to tune the optimizer, you take RMS prop, you take stochastic gradient descent, and this leads to actually different training processes. I'm just checking if everything is okay or if I have a question. Are you taking? So yes, the algorithm space now is actually the optimizers. So we fix the algorithm, it's going to be DQN, and we change the hyperparameters, in which case it's the optimizer. Cool, so we have a training process. Now what you can do is to see what it would look like if we try to control this training process. This is a method that we published at ICLR that we called adaptive deep Q network. And the idea is as follows. You take a target network, similarly to the baseline, which constitutes your first state. But this time, you're going to take several actions, or in other words, several hyperparameters. And you consider them all at once, and you look at the one that minimizes the loss the most, let's say the blue one, to continue the training. Now, this is at S1, so metastate 1. And to go forward, you can simply sample new hyperparameters coming from the working one. Again, you will actually have a new generation of agents. This is going to be the second state. And you're going to take the one that minimizes the loss again to continue the training. This means, contrary to the most common approach of population-based training, you don't need to have the performance of each agent. So if the loss of, for example, Q2 in orange works badly, you simply not evaluate it and you save some samples. That way you can be a lot more sample efficient. Let's look at the results. So here we evaluated our idea on 6 different Atari games with a budget of 40 million steps. So here it's the budget, and here you have the performance in the y-axis. We tried classical baselines, which are random search or Bayesian optimization. They indeed require more than one training run, which means that actually they are not sample efficient. Then we tried population-based training. As I was saying before, it's maybe slightly better. The problem is that you need to evaluate each agent in the population. So you are really wasting a lot of samples, especially the ones that have a very high loss. Maybe you don't want to evaluate them. In contrast, our algorithm only focuses on algorithms on hyperparameters that are actually yielding low loss. And this actually improves a lot the performances up to the budget and even further afterwards. Cool. I hope I convinced you that considering the immediate reward to control your algorithm is actually beneficial. I would like to insist on it because I think it's something that is very promising. Is there any question?
Did you guys average it over many runs?
This, you mean, did I do several seeds?
Yeah.
Yeah, actually, so this is on.
Yes.
I mean, you can see maybe the confidence interval. I think it's on 5 seeds as common in Atari games.
Right. Okay.
Thanks for the question.
On 57 tasks?
No,
tasks?
on 6 Atari games, 5 seeds.
Okay. Right. Okay.
Thanks for the question. So as I was saying, I would like to continue in that path because I think it's really something that can yield good results. One thing that I did not. Yes, sorry.
Also, sorry for interrupting. You said that it's computationally expensive. How did you dealt with this? As you're running multiple algorithms parallelly, right?
Yes, so that's a good question. So the main focus of the paper was to try to have a better sample efficiency. So here you can clearly see that it's more sample efficient. However, it's true that both methods, adaptive deep Q network and population-based training, they are training several agents in parallel, so they use more compute in terms of time. However, this can be parallelized because the training can really be parallelized such that it looks like you're only training one agent. And indeed, in the paper, in the appendix, we report the same graph, but the x-axis is this time the time. And actually, you can really see that the adaptive deep Q network is still outperforming the baseline, even if you consider the time and not the sample efficiency.
Also, I have one more question.
Yeah, go for it.
So, I mean, like, do you guys have some curriculum? Is it like the same task which you are sampling every single point of time from 3 different algorithms, or is it like 3 different tasks on 3 different algorithms?
It's the aggregated results on 6 algorithms. So here, what we do is we only consider one game, and we train, and then we report the performances. So those 3 different Q functions, they are trained on the same task, but one is trained with Adam, the other one with RMS prop, the other one with stochastic gradient descent, for example. Here we consider the very wide hyperparameter search space, so there's actually a lot more, including neural architecture search. Does that answer the question?
All right. I was just curious, I was just curious if we could do that as well.
So of course, a multi-task, it's something that we do not tackle in this paper, but it could be interesting actually to see what's the right balance between different hyperparameters and different tasks.
All right, sounds good.
Thank you. So let's dive into it again one more time. Now I hope I convinced you that actually considering the meta reward as a training loss is interesting. But one thing that is still missing, I think, with this method is, what if you have some knowledge that you prefer some hyperparameters to others? Let's say for some reason you prefer phi prime to phi. How can you deal with that? Because maybe you know that the reward is better. So do you sometimes choose one hyperparameter that you prefer and then take another time the reward that is better? This can happen if you look at, for example, hyperparameters that are setting the size of your neural network, such as the sparsity. So if you consider that instead of having the hyperparameter to tune, you tune the sparsity level of your agents. In other words, how many weights do you remove in your network? Sparse networks are usually very preferable to dense ones because they have a lower memory footprint. So this actually allows you to deploy your agent afterwards at a lower cost since it's using less parameters. Okay. So this is another method that we developed. I will explain the difference with adaptive deep Q network. So this is called O, the deep Q network, and we published it at RLC this year. The idea is very similar. You start with a target network, Q of 0, Q bar of 0. This constitutes your first meta state. And this time, instead of choosing the different hyperparameters, you choose different sparsity levels. And you choose the one that minimizes the loss the most as the next sparsity level to continue the training. One crucial detail is that we only take higher sparsity levels, or in other words, smaller networks when we continue the training. And that way, we are actually choosing or controlling the sparsity level of our agents during the training. Let me show you how it works in practice. So this is exactly the same idea, but applied to SAC, and it's not adaptive Q network, it's other Q network this time. So we evaluated SAC in a dense fashion, so without pruning any weights. This is the training in a number of million steps, and this is the performance. We tried to give, we tried to train a small network, a medium network, and a large network. I will report here the environment steps, and this is the sparsity schedule. So how much do we prune? If it's 0, we don't prune. If it's 1, we remove every parameter of the networks. So of course, the more you remove, normally the worse it performs. And here's going to be the final sparsity level, which is basically your cost of deploying the agent in the real world. 1 is, again, remove everything. 0 is remove nothing. We tried the state of the art, which is what we call polyprune SAC, because what you are doing here is you are doing a polynomial sparsity schedule during the training. So this is hard-coded, and it's a simple evaluation. So we evaluate the algorithm, or in other words, we train a SAC agent that is getting pruned during the training. You see that it reaches at the end a hard-coded value of 95%, which means that you only have 5% of the weights at the end of the training. You see that the training for the large network is performing very well, the same as the dense network, so it's a good news. Same for medium network. However, for the small network, you see that the performances are very bad at the end. And most importantly, at one point, you are here, you are seeing the performances going down, and since you are simply evaluating, you cannot do anything to prevent the algorithm from pruning more parameters and therefore reducing even further the performances. In contrast, our algorithm discovers a sparsity schedule, which is not too optimistic in the sense that it goes to a lower sparsity schedule. However, it yields a good policy after only one training run. So you don't need to tune the sparsity schedule. And you see it performs equally to SAC, which is the dense approach. One thing that I found very interesting is that our algorithm that we called AutoSAC is actually pruning differently for different environments, which also makes sense because different environments have different difficulty to prune. Now, if we give as input a bigger network to this algorithm, it's actually going to prune it more. And that's also natural, but we did not tell the algorithm, oh, be careful, it's a bigger network, so prune it more. It simply looked at the loss and understood that you can prune more, actually. And of course, it's even more pruned if you actually consider the large network. Okay, cool. So now I'm done with that. If you have any questions, feel free to ask. Otherwise, I think someone asked.
Hello, are you pruning both critic and actor networks or just the critic?
That's a good question. In this case, we really focused on the actor. I guess a similar strategy could be designed for the actor, but so far we really focused on the critic because it's the main motivation of the work at the beginning. Is that clear?
Thanks. Yes. Thank you.
Thanks for the question. Now, let's see if we can go beyond the immediate reward and actually try to anticipate the future. What I mean by that is if you are at ST and you are trying to think which action to take or which algorithm to take, maybe you can think about what if I'm actually anticipating the future and already tweaking the actions or the algorithms that I want to use at time step t+1 or t+k. This is very, very close to what roboticists or control people call model predictive control. You have a surrogate model, so you anticipate the future, and from there you control your algorithm. For that, I want to speak about what is this transition dynamics. I actually never spoke about it. In most cases, in reinforcement learning, a transition dynamics in this meta-MDP is actually, is there a question or?
I think it looks more like a planning method.
Yeah, it's true. It's true. It's a planning method. Yeah, I agree. So here, with this transition dynamics that we have, in reinforcement learning, usually the idea is to minimize a loss. So I spoke about Q-learning before, so you can think about it as this is the previous state. So it's ST and you want to get ST+1. So this is your target network, and you try to minimize the TD error to have your next online network. Another way to think about it, if you think about PPO, for example, this would be the loss, and this is the reference policy, and you want to have a new policy. So for that, most of the people, they consider this loss, and they try to find this point, which is the optimal, the minimum point. And the most prominent approach is to start with an initial guess, which is in most cases chosen as the previous best parameters that you got. So the target network for your DQN and the reference policy for PPO. And what you do is stochastic gradient descent or ADAM. So you're at theta t+1, you take a gradient step with the gradient, and then you update your current estimate. And the question I was thinking about, so is for sure after n gradient steps, you say, okay, stop, let's go forward now. So this is the target update frequency, this n here. And the question I wanted to look at is, can we actually choose which initial state you want to take? Why do we always want to take the previous best estimate? I guess an easy answer is to say that it's the only thing we have, and it's maybe the best estimate you have so far. But a recent paper that was called, the idea was to actually reset the initial guess to some random value. So instead of taking this idea, they just say, okay, let's reset sometimes the parameters, and it was to kick out the primacy bias that you might have during training. But what if you could be able to already be there by actually having some planning, so to actually guess which states you will be in, and to already optimize it such that you have already done n steps in this loss, in which case you can simply go closer to the optimal point earlier. Is the question? No. Okay. So for that, I would like to anticipate the future such that you can actually choose an initial guess or an action that is closer to the optimal state by already optimizing for it. And this is not so complex, actually, when you think about it, because at ST, what do you have? You have theta t, and you are optimizing for theta t+1. So you already have it. Why don't you use it? Because at one point you will stop and consider the next state. So why don't you already use it for the next state to optimize for theta t+2? And you can do it recursively, but in parallel. This would be the target network, this the online network, and you would consider the online network as a target network for the next iteration. This would allow you to pre-train your network such that when you actually consider them for real, you already have a good estimate of what would be a good minimizer of this loss. So all I'm asking here is, instead of minimizing this term, we would minimize the sum of terms. And this can be perfectly done in parallel. In other words, instead of searching this minimum, we will search for the sum of the minimum of the sum of those terms. This is a paper that we got accepted at TMLR, and I will present it at RLC as well in 2 or 3 weeks. So this time we considered a bit more tasks. So we considered the benchmark of Atari in 20 Atari games and Mujoko in 6 Mujoko environments. We evaluated DQN, implicit quantile network, for a stronger baseline, SAC, and for a stronger baseline, draw Q. This is the training advancement, and this is the performances all the time. As I said, we evaluated those methods. So we trained an agent, and we evaluated those algorithms by minimizing this loss. Instead, we tried to control by anticipating the future, by simply adding more terms to the loss to actually tweak the actions before taking them. And what we were very happy to see is that in each case, this iterated version that we call iterated Q network yields a better performance. So you have a clear sample efficiency gain. Same as previously, we also report in the appendix the same plots, but with the training time as x-axis, and we see that for sure we take more time because you have more a richer loss or a more complex loss. However, first, you can really see in the appendix that we are still outperforming the baselines. And also, if you would have an ideal computer with ideal parallelization, because those losses, they can be parallelized very easily with JAX, you would end up with the same training time. Cool. I hope I convinced you that it's also a fruitful idea to anticipate the future. And now I will go to the same idea again, but with a different ambition. When we published this paper, Iterated DeepQ Network, we thought it was a shame not to use it a bit more to do something else, because this loss is very rich, actually. So we were wondering if, instead of having independent networks here, could you actually share the parameters and only use the richness of the loss to anticipate the future and to have actually a good performing agent with only one network? I recall that here it would require K networks. And in general, you always need to have the target network and the online network. So the ambition here is to bridge the gap between target-free and target-based reinforcement learning. And for that, what we did is we first considered the target-based version, where you have a target network and an online network, similarly to every value-based RL algorithm. We also considered removing the target and only have the target-free approach. This would be the best, but you will see it's not performing so well. And then we considered an approach where we share the parameters. So it's basically a happy medium between having 0 targets and having a full target. Sorry, I'm just checking if there's a question. Okay. And another idea is to implement what we've just discussed. It's basically an iterated loss where you have this shared features that are taken as input, and you have just the last linear layers that are different, and learning the Bellman iterations as I just showed. So for that, we actually evaluated on 15 Atari games, where what we do is we show here the performances during training, we show the amount of parameters, and we show the area under the curve. The baseline is target-based, and of course, I mean, that's the goal, is to reach a good performance that is as good as target-based, having way less parameters. A first approach is to consider this target-free, but you see that you constantly drop performances. Actually, you drop each, on average, 10%. So it's actually quite hurtful. Sure, you divide by 2 the amount of parameters, but the problem is you really suffer from it. We found out that just the happy medium already bridges the gap a bit by simply keeping an old version of the last linear layer. But one thing that we were very happy to see is that by increasing the amount of linear heads of the network, you can really bridge the gap and even actually outperform the target-based version by around 5%. But the main point is that by using half of the parameters, you can actually have the same performance. And that's something we were very happy to see. Cool. So this work will be presented at the workshop at RLC in 2 weeks as well. I'm going to the last part of my talk, which is about learning the dynamics. But if there's any questions about the previous topics, please feel free to ask.
I want to ask about anticipating the future. You were trying to do planning, right?
Yes.
Given us, so how learning the dynamics would help? I mean, if you are learning the dynamics, you could probably plan based on the learned dynamics model.
Yes.
But
so
do you have a model defined? I mean,
that's a good question. So
model.
I will go for that in the next section, which is actually called Learn the Dynamics. However, in this section about anticipating the future, we try to actually just pre-compute, if you want, the next a surrogate version of the next state without actually having this concrete model in closed form in our computer. We simply try to anticipate the future by considering the future, if that makes sense. So very concretely, here, what I'm doing is, instead of considering one network, I'm considering several networks. And the only thing I'm doing is actually trying to minimize the loss such that this one is actually corresponding to the next state. And by doing that, I'm anticipating the future because I'm already considering that I will freeze this network to actually use this one.
Okay. All right.
Cool. Thanks for the question. But I will go actually for this idea of learning the dynamics. So this time, I don't want to have a surrogate version of the next state. I really want to have the dynamics to maybe do planning. So this is very ambitious because planning in this space is planning in the space of objects in your computers, and they can be quite big. A first approach that we did is to learn the dynamics of a training process and not a training decision process, in which case we are not considering any actions here. So we are just learning the dynamics of the training. But this is already very powerful. So what we do, I will explain why. What we do is we take as input the state of the training, and we try to output the next state of the training. This is basically a model-based version of the approach, and it allows you to continue to train after the training stops. Why? This is because when you stop the training, so when you stop interacting with the environment, when you stop doing gradient descent steps, what you have is you ended up in a state, in a training state, with your policy, your key function, and so on. But as you have learned the dynamics with a neural network, let's say, so this is a neural network, you can actually predict the next state. So keep improving your policy or your key function without doing any gradient steps, without doing any environment interactions, simply by rolling out your model that you have learned. This is why I'm arguing that you can continue to train after the training stops. Let me explain how to do it. It's very straightforward because model-based RL is usually very close to supervised learning. As I explained before, this is what you usually do to get the next state. So you minimize a loss by doing gradient descent. So you start with theta t, and then you do a stochastic gradient descent step. So what you can do is to try to see if you can learn this model. So you take as input the previous state, which is theta t. You learn some neural network that I call gamma to output the argmin of the loss, which is basically this thing. So the only thing we did in this paper that we presented at AAAI is to learn a parametric model, a parameterized model, which is in that case a parameterized projected Bellman operator. That takes as input some parameters of your state and tries to output the next state, so n gradient steps afterwards. Okay, so what we did is we considered a benchmark that is called, it's a task that is called bicycle offline. You have here the performances and here the iterations. The iterations are very easy to understand. It's basically the T that you see here. And we ran DQN for some times, showing the optimal performance. And we tried our projected Bellman operator that we called PPO. And unfortunately, it was not better. But as I said, we have learned the model. We have learned how to go from one state to the other in the training. So no one prevents us from continuing the training without doing gradient steps, without interacting with the environment. And actually, by rolling out this model, we were able to match and even slightly outperform the baseline. So we were really happy to see that this can actually work. This is all for today. So thanks a lot for your attention. I hope I convinced you that we can control our algorithms, and it's maybe much better than trying to evaluate them. I would like to thank my collaborators, and if you have any questions, Feel free to ask.
I just want to see if I understand the last section. You are
Yes.
learning, like your state is your parameters, your network parameters,
Yeah,
and you are learning to how they like behave on during the time, like
exactly. So
check.
making sure it's clear, this is so this paper belongs to the field of deep weight space, where you take as input, as I showed here, the weights of a neural network, and you output the weight of a neural network. So the neural network that you learn is a hyper network that takes as input weights of neural networks and output weights of neural networks. However, this is a design choice. You can also choose to represent your Q functions, your policy, in a different way. And then you would have to learn a mapping from basically the representable mapping, that the representable way that you chose to the same space.
Okay, and how big is the like? How many parameters are those?
Yes,
that
so
you're
one limitation of this approach is that if you choose to represent your policy, your neural network, and whatnot with this with a neural network, the number of parameters of the projected Bellman operator or the hyper network here is quite big because it maps networks to networks. However, this is a problem that is often tackled in the space of deep weight spaces, because they basically do that all the time. They can take as input neural networks and they output something else. It can be neural networks, but it can be also just the performances. And we did not consider that because it was a first approach and we thought it was ambitious enough not to consider it. But there has been a lot of techniques that are trying to minimize the burden of this curse of dimensionality.
Thanks. Now I understand better.
Thanks.
Also, can you go back to the learning the dynamics method?
Yeah.
So you were talking about this theta. I mean, are you taking one network at a time, or is it like a you know set of networks?
Very cool
Like you have
question.
critic network.
Yeah, very cool question. So actually, what we are learning is the model. So the model takes as input a set of objects and output set of objects. But if you want a good model, maybe you don't want to only learn it on one trajectory. So what we do actually in this paper, I mean, what we consider is actually to learn this model on the various states, if you want, and not only one. So we take them in parallel. So of course, this increases a bit the computational complexity, though it does not increase the number of gradient steps that we take or so. We really try to be fair with the baseline and the number of samples that you take. But it's true that it's a possibility to actually learn this dynamics model on more than one state, if that makes sense.
Oh, I mean, so every state consists of certain elements like policy, critic, network, right?
So it's true that in theory it's like that. In practice here, what we chose is just to take the target network, and that's it.
Target policy network or a critic network?
So here we are comparing against DQN. We were staying in discrete action spaces. Okay. So it's really just the target network. So here, what it tries to predict is the sequence of target networks, actually.
Okay, right. And also, you are trying to learn this dynamics model, right? So
yes.
Don't you think you're gonna have this problem of model bias?
For sure. You can have it. I mean, indeed, you have it here. At the beginning, for sure, you are not as good as DQN. However, as I said, the big benefit of it is if you want to continue the training, well, you can.
Okay, so is it a single model you're training, or you have an ensemble of?
No, this is a single model. The confidence interval you see here, it's basically because we did several seeds. So at the end, we learned several models, but just to see the consistency with randomness.
Okay.
Thanks for the question.
Do we have more questions?
I have one last question.
Yes,
Is
please.
your dynamics model is like generalizable? Like you can you are training for many seeds, né? 5. From one seed, it can use the network from the other.
That's a good question. So it's interesting because usually the question I get is, can it generalize over several agent MDPs? So I just want to clarify that. It's not, you cannot generalize over several agent MDPs because you are learning the model of the training dynamics that are behind the hood. They are actually linked to the reward function and the dynamics of the agent, of the environments. However, I would expect, we did not try, so I don't know, but I would expect that it generalizes over seeds for sure. Thanks for the question.
Thank you for the answer.
So how many iterations? Is that 18 iterations? That's it?
Yes, so here it's only 18 iterations. It's true that if you compare with the amount of target updates you do on Atari games, it's a lot more. Again, this was really just to show that the idea works or can work, and to scale it up to a larger amount of iterations. I mean, actually, in the paper, we also show, if I'm not wrong, we did that for the rebuttal on Atari games, and it also works. Though the method needs to be adapted because maybe just want to have a model that is good in a specific space and not everywhere during the training. If that makes sense.
Also, I feel like your model would overfit because you're using a single model, right? And then probably it is prone to generating model errors.
I know for sure. For sure, it's prone to it. I think there's different ways to do it. So I guess you are going towards the idea of having an ensemble of models. I think one other way to do it would be to actually, and that's actually what we do here, is to consider several trajectories. However, as I said before, we are not evaluating each trajectories. I mean, here it's completely offline, so we are not evaluating anyone. But the idea would be to actually make the model more robust by actually considering several theta t's at the same time.
And this theta t is, this space is pretty big, you know?
Yeah.
Right. How are you even generalizing over that is pretty hard, isn't it?
Yes, but as I said before, the goal in general is not to generalize. When I was presenting the main motivation, the goal is to reach a good policy after a single training step. So if it cannot be reused other than just extending the training, it's also fine because the goal is really to be good at, sorry, I just want to make sure, to be good at one training trajectory, not more.
Okay, right.
Thanks for the question.
Yeah, so if we don't have more questions, we can wrap up the session and thank the speaker.
Thanks.
Thanks for joining us, Theo. It was great. I mean, if anyone has more questions, definitely I would say he would be open, to take
feel free to reach
offline.
out. Yeah, for sure.
Yeah, you can actually reach out to him via email.
Yeah,
so
for sure.
Pretty okay. Yeah. Thanks for joining again.
Thank you.
It was great. It was fun.
Thank you for inviting me.
Thank you.
Bye-bye.
Bye.